All right, let's talk about something we all use every single day, streaming video. I mean, services like YouTube, Netflix, they're just part of our lives now. But have you ever stopped to think about the insane technology that makes it all work? Today, we're going to pull back that curtain. Let's get right into it. I mean, think about it. You've got a movie file that could be, 100 gigabytes? It's absolutely massive. And yet, you click play and poof, it's right there on your TV, instantly. How in the world does that happen? It seriously feels like magic, right? Well, it's not magic, but it is an incredibly clever step-by-step process. And that's exactly what we're going to break down today. The entire journey, from the moment a camera captures something all the way to your screen. Okay, so where do we even start? Well, you can think of the whole process like a digital media assembly line. And the very first stop on this line is all about translation. We have to take the real world, the actual light and sound that we see and hear, and convert it into a language that computers can actually speak. And this right here is the fundamental challenge. See, the world we live in is analog. It's a smooth, continuous flow of information, kind of like that smooth wave you see. But computers, they're the exact opposite. They only speak digital, a language made up of separate, distinct steps, basically just zeros and ones. So step one for every single video, every piece of audio, is figuring out how to translate that smooth analog world into these chunky digital steps. And that whole conversion process, it's got a name, digitization. And honestly, this is the foundation for everything else we're going to talk about. A great way to think about it is like this. You're taking something infinitely complex, like a sound wave or a beautiful image, and you're creating this super detailed dot-to-dot drawing of it. It's a drawing made of numbers that a computer can finally read, save, and mess with. Okay, so we're making this dot-to-dot drawing, but how do we make sure it's actually a good drawing? A perfect copy of the real thing. Well, that brings us to our next big challenge, making sure we capture just the right amount of detail. Let's zoom in on audio for a second. How do you take a smooth, beautiful sound wave and turn it into a bunch of numbers without it sounding, terrible? The secret is all about how often we check in on that wave, how many snapshots we take of it. And this is what we call the sampling rate. Just picture it. You're taking thousands upon thousands of little snapshots of that sound wave every single second. It's pretty straightforward, really. The more snapshots you take, the more detailed and true to life your digital copy is going to be. And we measure that in a unit called hertz. So, the big question is, how many snapshots is enough? Is there a magic number? Well, yeah, there kind of is. It comes from a brilliant idea called the Nyquist-Shannon theorem. And it basically says this. To perfectly capture a signal, your sampling rate needs to be at least twice the highest frequency you're trying to record. The tracing analogy is perfect. If your dots are too spread out when you're tracing something, you end up with a clunky, jagged line, right? But if you put your dots at least twice as close together as the tightest curve on the drawing, you can connect them and get a perfect replica of the original shape. It's the same exact principle with sound waves. Let's make this real. So the absolute highest frequency a human can typically hear is around 20,000 hertz. Okay, so if we use our times 2 rule, what's 20,000 times 2? 40,000. That means to capture everything a human ear can possibly hear, we need to sample more than 40,000 times per second. And guess what? That is exactly why the standard for an audio CD was set at 44,100 samples every single second. It's not a random number. All right, awesome. So we've digitized our audio, we've digitized our video. We're done, right? Not even close. We have a huge problem now. The files are gigantic. I'm talking impossibly, unstreamably massive. Way too big to ever send over the internet. So this brings us to what is maybe the most important step on our whole assembly line. We've got to shrink these things down. We need compression. The tool for the job here is something called a codec. And that name is actually a mashup of two words, coder and decoder. All a codec really is a super smart algorithm, a set of rules that figures out how to compress the file to make it really small. And then on the other end, it knows how to decompress it or unpack it on your phone or your TV. And I am not exaggerating when I say this. Without codecs, streaming video would literally not be a thing. It just wouldn't work. So there's a whole family of these video codecs out there. You've got H.264, which is kind of the old, reliable workhorse. It plays on basically anything, anywhere. Then you have its successor, H.265, which is about 50% more efficient. You kind of need that for big 4K video. And now, the new kid on the block is AV1. It's even more efficient, and the big deal is that it's royalty-free, which is why big players like Google and Netflix are all in on it. So if you're an engineer at one of these companies, you've got this constant balancing act. Do you go for the one that works everywhere, the one that's the most efficient, or the one that saves you a ton of money on licensing fees? It's a huge decision. And this is what it actually looks like in the real world. An engineer would use a tool like FmpEg and type in a command just like this one. Now, don't let it scare you. It's really just a recipe. It's telling the computer, hey, take this big input video file, use the H.264 codec to compress it, and then spit out a new, much smaller file called output.mp4 that's ready to go on the internet. That's all it is. And of course, it's not just video. Audio needs to be compressed too. The big one you interact with all the time, probably without even knowing it, is AAC. That's the standard for YouTube, for Apple Music, pretty much all major streaming. You've still got the classic MP3, of course, and then there's a really cool modern one called Opus. It's amazing for things like Zoom calls or FaceTime because it's super flexible and can adapt on the fly if your internet connection gets a little shaky. Okay, check this out. We've got our compressed video file, we've got our compressed audio file, but they're two separate things. We can't just send them out like that. We need to package them up together so they stay in sync. And the best way to think about this next step is like packing a lunchbox. That lunchbox is what we call a container format. You see these all the time. Anytime you see a file that ends in .mp4 or .mkv, you're looking at a container. The container itself isn't the video or the audio. It's the box that holds everything together. It's got the video stream, the audio stream, maybe multiple audio tracks for different languages, subtitles. It's all packed neatly inside, perfectly synchronized. And which lunchbox you choose really matters. MP4 is fantastic for the kind of videos you watch on YouTube, on-demand stuff. It's super efficient. But for live streaming, like a sports game or a news broadcast, you'll almost always see something called a transport stream, or TS. Now, why the difference? Well, TS is designed to be really robust. It breaks the stream into tiny little independent packets. That way, if your internet connection glitches and you lose a few packets, it's no big deal. The rest of the stream just keeps on chugging along without the whole thing crashing. It's built for resilience. And just like the compression, engineers can swap these containers around super easily. You can run a command like this one here. See that -C copy part? That's the key. It tells the computer, hey, don't redo all that hard work of compressing the video again. Just copy it. Just take the food out of this lunchbox and put it into that other lunchbox. It's a really fast and simple operation. We are so close to the finish line. We've got our compressed video and audio, and it's all neatly packaged inside our container. There's just one last decision to make before we can send this thing out into the world. We have to decide exactly how much data to send to the viewer every single second. And this is known as the bitrate. You can think of it like a data budget for each second of video. It's a simple trade-off. If you have a high bitrate, you're sending more data per second. That means the quality is going to be higher, clearer, crisper, but it also means you need a better internet connection to handle it. A lower bitrate, on the other hand, means lower quality, but it's a much smaller file that's way easier to stream on a slow connection. Now, there are two main ways to handle this data budget. The first is constant bitrate, or CBR. It's like a leaky faucet. It sends the exact same amount of data every single second, no matter what's happening on screen. It's predictable, which makes it good for live streaming, but the much smarter approach is variable bitrate, or VBR. This is way more efficient. It gives a bigger data budget to complex, fast-moving action scenes, and then it saves data on simple, static scenes, like someone just talking against a plain background. For on-demand video, VBR is pretty much always the way to go. And all of this leads us to the real secret sauce of modern streaming. This is the magic right here, adaptive bitrate streaming, or ABR. Here's how it works. When I upload a video to YouTube, it doesn't just store one file. It creates a whole bunch of different versions. A 4K version with a high bitrate, a 1080p version, a 720p version, all the way down to a potato quality 240p version. Then, your video player on your phone or computer is constantly talking to the server, checking your internet speed, and it intelligently and automatically switches between those different versions to give you the absolute best quality you can handle without buffering. You've seen this happen a million times. It's why your video might start a little blurry and then suddenly snap into sharp HD, or why the quality dips for a second when your Wi-Fi signal gets weak. That's ABR in action, saving you from the dreaded buffering wheel. Okay, that was a lot, so let's take a deep breath and quickly recap the entire journey, putting all the pieces together one last time, from camera to screen. It all comes down to that 4-step digital assembly line. First, we digitize.
We turn the analog world into numbers by sampling it thousands of times a second. Second, we compress. We use a smart codec like H.264 to shrink those huge files down. Third, we package everything, the video, the audio, the subtitles, into a container like an MP4. And finally, step 4, we stream. We send out all those different adaptive bitrate versions, and your player intelligently picks the right one for you. That's the whole process.
So there you have it. It's not magic, it's just this incredibly elegant dance between codecs, containers, and bitrates. Honestly, the next time you see that little buffering icon, that spinning wheel of doom, I hope you'll look at it a little differently. Now you know exactly what's happening behind the scenes. It's this whole complex system just doing its absolute best to get that digital lunchbox delivered to your screen. Thanks so much for joining me.